Hello, everyone. Welcome to the lecture on acids and bases. This is from chapter 14 of Zumdahl. For everyone, what you need to have out is the flowchart you see in the picture, along with the problems that I gave you in the packet. This video, I'm going to go over how you work on all of those questions. Hopefully, it'll make chapter 14 make more sense. I already gave you some instruction or a video on pH, POH, hydrogen ion, also known as hydronium ion and hydroxide ion calculations. I'll go over that again here. And then we're going to deal with an acid in solution or a base in solution, both strong and weak. So I hope everyone is doing well at home and that you have time to get some work done here so we can keep moving forward. I don't know what's going on yet with the AP exams, so we're just going to keep moving along. I'm going to say goodbye so that I have the whole screen to explain everything. Of course, if you have any questions, just email me and I'll get back to you and we'll see how it goes. Let's get started. Okay, let's take a look at this flow chart. You have a picture of it you have a handout of it rather at home. And what I wanted to point out is that as soon as you have one of these four, the hydrogen, hydroxide, the POH, or the pH, of course you can find the other three. They're connected, right? pH is minus the log of the hydrogen ion concentration, POH minus the log of hydroxide, pH plus POH equals 14, and then of course Kw, which is 1 times 10 to the minus 14, is equal to H plus or H3O plus times OH minus. We'll go over a few problems in a minute, but there is that connection. The other thing I wanted to point out, and I know I had mentioned before we're home here working, is that chapter 14 has to do with this left-hand side of this flow chart. We're dealing with one substance in water, whether it's an acid or a base or a salt. Chapter 15 is when we're going to go to the right-hand side. Nice 15, Ms. Mack. Let's just take a look at the flow chart so you know where we're heading, and then we're going to work on those problems from chapter 14 I gave you in the packet. If I scroll down, we are dealing with a strong acid or a strong base. Your strong acids, remember there are 6. We use CBS pen. I'll show you on the next page. In other words, though, we have an acid that completely breaks apart, so our acid concentration is going to give us our hydrogen ion concentration, which then can give us anything else we're asked. With bases, anytime that I have my active metals in OH, they completely dissociate or split apart. And again, I'm going to have my, let's say, sodium hydroxide ion concentration, which will give me my my hydroxide ion concentration, which will give me my POH, and I can go to pH. The strong acid, strong base calculations are straightforward, but when we get to a weak acid or a weak base, now we have to deal with equilibrium again. So if I scroll up a little bit, on the acid side, the problem that shows up the most would be, or the example acid that shows up the most, and we're going to go over, would be something like acetic acid. You have your stoichiometric thing, you have your equilibrium thing, and you can see here in the box it says use Ka/ICE to find H+. Ka, that's the ionization constant for the acid. It's going to be less than 1 because weak acids would rather stay as the molecule than to split, although it splits a little bit. ICE, remember, is that chart. That's your initial concentrations, your change, and then your concentration at equilibrium. And then on the base side, the typical weak base that we use would be ammonia, NH3. And we're going to use a Kb value now. That's ionization constant for a base, our initial change, equilibrium, or ICE chart, and find hydroxide. And there is a way, or a calculation rather, if I have Remember, an acid, I have a conjugate base. If I have a base, I have a conjugate acid. And Ka times Kb is equal to Kw. We're going to need that, not necessarily right now in chapter 14, but we'll take a look at that in chapter 15. Now, one other thing to note that really isn't on this chart is when I put a salt in water. It could be neutral, it could be acidic, or it could be basic. It's going to depend on when the salt dissociates, what I get in solution. Do the ions in solution react with water? And if they do react with water, now we have an acidic or basic situation. We'll take a look at that too. So get out the rest of those questions and let's go through them. Okay, so the chapter 14 problems that I gave you that we normally do in class, we're doing here now. You can check the handout that I gave you if you want to go through the problems for yourself and just check and see if you got them right, or if you have to come back if you're not sure how I got to an answer. Otherwise, just double check. If you're getting them correct, then you're doing great and you don't have to listen to me. Otherwise, you might want to listen here and make sure that you have everything. First of all, the 6 strong acids. Sometimes people say 7. CBS pin, remember this is a little misleading because the P here is for perchloric acid, not for phosphoric. Phosphoric is a weak acid. These are known as the 6 strong acids. Sometimes chloric acid is also considered, it's on that cusp of being weak or strong, and that's where the 7 comes in. But I like to do the 6, and here they are. Now, pH of 0.0020 molar HCl. Hydrochloric acid, as soon as you recognize it's a strong acid, all you have to do is use the pH equation, plug it in, hit the log key, change the sign, and you have the pH. Fairly straightforward. Let's go to number 2. For the second question here, we want the pH, but now we have a strong base. If you recognize sodium hydroxide is one of the strong bases, right? Our group 1 metals and OH are strong. Calcium hydroxide, for our class, we consider it a strong base. Some others might consider it weak. And then the elements below calcium. So any other metal in OH is weak, including ammonia, which is a weak base. All right. In this question, we're talking about orange juice. We have a pH of 3.80, and you're asked the H plus and the OH minus concentrations in the juice. Before I forget, anytime I have a solution, water, of course, being the solvent, there's always going to be hydrogen and hydroxide ions. You're not always asked to figure out the concentrations, but they are present. Even the strongest acid. And by the way, another thing that I should mention, the pH scale, it goes less than 0. It can go into negative territory, and it means it can be higher also than 14. So 0 to 14 or 1 to 14 is usually what we're dealing with as far as a pH range, but it can go higher and lower. All right, so for question 3, a couple of different ways you can do it. What I did was I took the pH, I found the hydrogen ion concentration, and then I used Kw is equal to H plus times OH minus. Now the ionization constant for water is 1 times 10 to the minus 14. That is on the reference table. Plug in the hydrogen ion concentration, get hydroxide. You could have, of course, taken pH plus POH is equal to 14, figure out POH, and then you POH is equal to minus the log of the hydroxide ion concentration. Remember that box in that flow chart. If you got 1, you got all 4. Doesn't matter what direction you go. All right, now we get to question 4. I do have a typo for 4 and 5. For some reason, I forgot the H for acetic acid. So you're just seeing the acetate ion in the parentheses, but that's wrong. It should say HC2H3O2. We have a weak acid here. It's not part of CBS pin. We have a Ka value of 1.8 times 10 to the minus 5. We know that's a number fairly less than 1. That means that acetic acid would predominantly stay together as opposed to break apart, but some of the molecules do ionize. When we want to figure out something like pH, just like any other equilibrium we did in chapter 13, there is my equilibrium thing, and then there's my stoichiometric thing. You need your ICE chart, and you need your equilibrium expression. We started with 0.1 of the acetic acid, no hydrogen ions, and no acetate ions. Then there was a change. We dropped in concentration of the acetic acid while building in the concentration of the hydrogen ion and the acetate ion. Then, once I got down here, my 0.1 minus x, my x and my x, now I'm going to go ahead and substitute that into the equilibrium expression. And remember, we have this Ka value. One other thing, we're going to do an assume, and then we're going to do a check. As long as the ionization of whatever we're starting with is 5% or less, it's said to be a good assumption. So we're going to assume that 0.1 minus x, the x is going to be so small that we're not going to see a change in the initial concentration of the acetic acid. I substitute in, I solve for x, and I get a x concentration of 1.3 times 10 to the minus 3. I'm not done. Remember, we were asked what's the pH. I have to go ahead and put that into the expression. I get a pH of 2.9. And then finally, you should check to make sure that it's less than 5% as far as ionization, which I'm just taking now the concentration of the H plus, dividing it by the concentration of the acid to start, times 100, and we're good. This is a classic weak acid calculation. I would recommend doing it more than once to make sure you have this down. It's also good practice really for chapter 13 as well. It's just now we're dealing with an acid that's breaking apart. Let's move on to 5. And as a matter of fact, if you think you know how to do question 4 fairly well, you might want to work through this question first. It's the same setup. It's supposed to be acetic acid. I had a typo, 0.5 molar now as opposed to 0.1. Everything else is the same. However, you're asked, or what are the concentrations of all the species? This is where also the hydroxide ion and the acetate ion, you would have to list that as well. We're following the same format as above. We have our ICE chart, we have our equilibrium expression. Once we get our concentrations at equilibrium, we substitute in, we solve for x. We do our assumption, we do our check, and now in order to get all of our concentrations here, of course our hydrogen ion concentration and our acetate ion are the same values, but we need to get hydroxide. In this case, I just use Kw is equal to the concentration of H plus times the concentration of OH minus. If you're getting anything wrong, my suggestion is, if you understand how I solve for it, leave it alone. Go get a beverage, take a walk, come back hours later or the next day and try it again for yourself. Remember that these are my lecture problems that we go through typically in class. This is the backbone, if you will, of the acid-base chapter. Very important that you know how to do these so then you can work on anything else that might be thrown your way. All right, for ammonia. Ammonia in water forms the ammonium ion and the hydroxide ion. We have 0.1 molar ammonia, and we're looking for the pH. Well, ammonia is a base. Notice we form the hydroxide ion. That's part of Bronsted-Lowry theory. Ammonia accepted H plus, water in this case, to start on the left as a base. Then we form the conjugate acid, the ammonium ion, and the conjugate base, the hydroxide ion. Since water is a pure liquid, we don't have to worry about that in our ICE chart, and we end up with 0.1 minus x for ammonia, x and x for the ammonium ion and hydroxide. At the same time, here we have our expression, our Kb expression. Now, it is a coinkydink that the value for Kb for ammonia at 25 degrees Celsius is 1.8 times 10 to the minus 5. And yes, that might look familiar because the Ka value for acetic acid at 25 degrees Celsius is 1.8 times 10 to the minus 5. but that is a coinky dink. Don't think that every weak acid or weak base are going to have the same K value. That's not going to happen. And by the way, this would have been given to you, or you would look it up in the textbook. Well, here we go. We have our ICE chart. We get our concentrations at equilibrium. We're going to substitute them into the equilibrium expression. We're going to have our assume again. We solve for X. That gives us the hydroxide ion concentration. We do our check, less than 5%. Now we get POH, or that's how I did it, POH from the hydroxide ion concentration, and then use pH plus POH is equal to 14, and found the pH to be 11.1. Makes sense, it's a base, so you would expect the pH to be greater than 7. That's the other thing. As you do these problems, if you anticipate what the answer is going to be, that's going to really, really help you try to catch any mistakes. These questions, they're not overly difficult at this point, but you want to stay organized and you want to make sure that as you're writing it out, that somebody else, for example, myself or your teacher or the person that's going to grade your test, understands exactly what you were doing. Let's move on to question 7. All right, for question 7, now I have the 0.1 molar acetic acid, and I'm given the pH to be 2.88, which means I can figure out the hydrogen ion concentration, and I'm asked to calculate Ka. Well, I need my equilibrium expression. You see it here, but to fill it in, I have to go over. And notice I keep writing the equation and then putting the ICE chart right underneath. Stay organized. I got 0.1 molar acetic acid. I don't have hydrogen or acetic acid, the acetate ion to start, but I figure out how much of the H plus that I'm making from the pH. That also gives me then the acetate ion that is in solution and how much of the acetic acid, right? How much dropped in concentration. So I have my equilibrium concentrations here, which I'm going to go back and substitute into the equilibrium expression. When I go ahead and I solve for K, I get 1.7 times 10 to the minus 5. As far as percent dissociation, right, the top is going to be the change. In this case, I just labeled it as H plus, and the bottom is the concentration of the acid I started with times 100, and it's 1.3%. This might look familiar to you because we use it for the check when we make the assumptions, right, for the other problems we've done. So, of course, percent is always part over the whole thing times 100. We want to know how much of the acetic acid actually broke apart. All right, moving on to question 8. This is the last question in this chapter 14 lecture to do, so let's check it out. All right, in question 8, now we're given the weak base. We have the ammonia concentration, and we're told that ammonia has gone through 4.2% ionization. So 4.2% of the ammonia has changed into the ammonium ion and the hydroxide ion. All right, well, I need to figure that out. You can see down here that my X, if you will, is going to be the change. I have the initial concentration of the ammonia to start, and it was a 4.2% change. Here is the answer. That goes into my ICE chart, and now at the end I have my concentrations, and when I go ahead and I put that into the equilibrium expression, get the Kb value of 1.8 times 10 to the minus 5. Well, that is it for my lecture, if you will, on chapter 14. If you have any questions, just email me. We'll tackle this together, and I will talk to you soon.